For my project on the motion of a falling object, I dropped a stuffed bee from a balcony. I then recorded the motion, obtained real position and time data using the program tracker, and compared the actual motion with predicted motion using implementation of Newton's second law in two computational models, one only accounting for the effect of gravity on the stuffed bee, and the other adding in the force of drag. Newton's second law says that force equals mass times acceleration, where acceleration equals change in velocity divided by change in time. Knowing that change in velocity equals final velocity minus initial velocity, it is possible to predict the future motion of an object by rearranging this equation to give final velocity equals initial velocity plus net force divided by mass times change in time. My stuffed bee accelerated downwards over time as it fell. This means that the velocity increased, and net force on the system, the bee, was not zero. In order to obtain real position versus time data, I chose a conventional coordinate axis system, with the downwards motion of the bee being in the negative y direction. I chose to track the position of the nose of the stuffed bee, because it was easily discernible in each frame of the video. I put the origin of my axes at the nose of the bee in the first frame analyzed so that the bee's initial position was 0, 0 meters. You can see that I also tilted my axes slightly so that the bee fell straight down along the negative y-axis and movement in the x direction would not be present, so it would not need to be considered in determining velocity. To orient the axis in the correct units, I measured the length of this strip of wood to be 0.146 meters and inputted that data. I analyzed the entire motion of the fall, which happened to be frames 48 to 61. I oriented this such that frame 48, the time of first observation, would be 0 seconds. Frame 61, the time of last observation, was 0.433 seconds later. So Tracker gave me this position and time data. The next step was to compare this real data to predicted data using computational models that use Newton's second law. Referring back to this mathematical representation of Newton's second law and knowing that net force will include either gravity or gravity and drag, what I wanted the code to do was calculate the position of the ball at each time step and update velocity at each time step too. I wanted the program to run this calculation repeatedly, updating the initial position at each time step to be the final position from the previous time step, and the velocity at each time step to be calculated using the final velocity from the previous time step as the new initial. Let's take a look at the code and see if we can clarify this a bit more. This portion of the code sets up the initial conditions needed for calculation using Newton's second law: mass, position, velocity, and time of first observation. I calculated the initial velocity using the first two position and time points given to me by Tracker. I also had to set this time step delta t, setting it small relative to the total observation time to obtain enough data points for a smooth curve and to have many velocity updates. This piece of code is the calculation loop, which repeatedly applies Newton's second law of motion. This loop calculates the position of the bee for every point in time between 0 seconds and 0.433 seconds at 0.001 second intervals. Net force is the sum of all forces acting on the system. First, let's assume that gravity is the only force acting on the system, so that net force equals weight force, which is equal to the bee's mass times 9.8 newtons of force per kilogram, times the direction of the force, which in this case is in the negative y direction. As you can see, velocity is updated with each pass through the loop, and so is the position. When I run the code, here's what I get. The yellow arrow represents the force of gravity on the system. This code works the same way as the previous model, except that net force is now the sum of weight force and drag force. The model of drag force used is called turbulent drag, where the drag force is proportional to the square of the speed of the object. The phrase "is proportional to" implies that there is a constant scalar involved in the relationship between the variables. I have named the scalar b in the code. I manipulated the value of b until the final position in the model matched up with the experimental final position. When I run this code, a yellow arrow again represents gravity, and the blue arrow represents the force of drag acting on the system. Putting both models onto a graph of the real data, we can make comparisons. It is important to remember that the initial velocity is not a prediction because it was written into the code, so both models will match the experimental data at the beginning of the graph. Additionally, the drag model will also match at the end because it was also written into the code through the use of the scalar b equals 0.453. While the model with only gravity fails to predict the position of the bee as the time elapses, the model with drag does a great job of predicting the position of the bee throughout the entire time interval. Here's a graph of velocity versus time of my models with and without drag. You can see that the velocity of Model 1 appears linear, with constant acceleration. There's nothing limiting the growth of the velocity with this model. Model 2 velocity appears to be approaching a limit, as it is curved and becoming more shallow in slope. This limit is likely terminal velocity. Because it is limited by drag, it approaches the maximum velocity at which an object can fall. If the stuffed bee were intentionally thrown downwards, terminal velocity at the drag model would be the same. Here it is in computer model form, where the starting velocity is -3 meters per second, instead of falling from rest at 0 meters per second. I also changed the delta t value to be 0.05 seconds, and I made the total time interval longer. You can see that the velocity of the model including drag levels off at the same terminal velocity, whereas Model 1, including only gravity, continues to increase indefinitely.